Hello and welcome back. This is Lecture 3 in the Thermodynamics course. The two primary topics that we're going to go over today are principles in thermodynamics, and then we're going to also spend a lot of time looking at isentropic analysis and how a meteorologist puts together an isentropic analysis. We'll start with looking at a definition of work. Work is the force applied over a distance. The equation for work is force times distance. Work can also be related to the pressure and volume through the equation the change in work is equal to pressure times the change in volume. And on the overhead we'll take a look at work and some diagrams. Here's our equation. Work is force times distance. So if we have a mass here and we move this mass, the work is equal to that force that's applied to this mass times the distance that it moves. Or we could have pressure times a change in volume is the work that's done on this, for example here, parcel of air. Next we'll look at the concept of geopotential height. This is a term that you've often heard before, and when looking at the weather charts, such as the upper air charts, it has a geopotential height and not regular height, so we'll go over what the difference is between regular height in meters and geopotential height in meters. First, starting off with what is geopotential. Geopotential is the work that must be done against gravity to lift a mass from sea level to a particular height in the troposphere. When air is forced to move a vertical distance, then work is done on that air in the direction the force is acting. A geopotential meter, how that is found is by taking the ratio of actual gravity to average gravity and then multiplying that by the number of meters. The average value of gravity, we'll call this G star, is 9.8 meters per second squared. But although we're using this value as a constant in the class, it actually varies with latitude and height. So this is why the geopotential height is not exactly equal to the actual height, because there is that slight variation in gravity. So at the bottom there, how to find a geopotential meter is you take that ratio, so you take the actual value of G, divide that by the average G, and then multiply that by the number of meters. We'll look at an example of this on the overhead camera. On finding geopotential height, suppose that the actual height is 4,000 meters. And at this location, we calculate that the value of gravity is 9.78 meters per second squared. And we want to find what is the geopotential height. So we take that ratio, as we saw on our PowerPoint, our 9.78 is our actual, divided by the average gravity, the 9.8, and then multiply that by 4,000. And once that is done, we get 3,992 geopotential meters. So you'll see that the difference between geopotential meters and actual meters isn't that much. And again, that difference is accounted for because of the difference in gravity. Next, we'll look at heat. Heat is energy transfer due to a temperature difference. Nature is always aiming to distribute heat until a balance is achieved, and this is the reason why we have circulation in the atmosphere. We have excess heat near the equator, deficit heat at the poles, and over time the air tries to distribute that energy to try to balance it out. When a system is not in balance, excess energy moves toward the deficit energy. And we'll also look at an equation for thermal motion. On the overhead, we'll take a look at an example of heat transfer. Suppose that we have a fire, and above this fire we have a metal pole. Immediately above the fire, this metal pole is going to be heated, but the temperature is going to be warmer where the fire is in direct contact with this metal pole. But that heat is not just going to stay above where it's warming up the metal pole. That heat is going to travel along the pole, and it's going to travel from the warmer temperatures towards the cooler temperatures. So heat transfer is always from warmer towards colder air, because it's trying to distribute that heat. There's an equation for thermal equilibrium that's covered in the textbook. And this equation is a specific heat constant times the mass times the final temperature minus the initial temperature. And the number of terms that you could have 2, 3, or more terms. And what we mean by thermal equilibrium is we have more than one object or mass coming into contact with each other, and then we're determining what the temperature is after it comes into equilibrium. So if you have a warm object and a cold object, then the warm object is going to cool down and the cool object is going to warm up, and they're going to come to a equilibrium temperature eventually. So this is the equation that's used to find that. And the textbook, it'll give this equation here, capital C1 times the final temperature minus the initial temperature plus C2 times the final temperature minus the initial temperature of the second substance. And what I have here is how to algebraically reduce this equation down to where we just find the final temperature. Because that's what, when we're doing these thermal equilibrium problems, that's what we're trying to find, is what is the final temperature of the substance. If this is a little hard to see, I'm going to include all these diagrams that I'm using in all my lectures so that you can have them to follow along. And what we do here is we distribute these terms out. So we take the C1, which the capital C1 is equal to the mass times the specific heat constant. So we multiply C1 times TF and then C1 times T1, and that accounts for those two terms there. And then we distribute the C2 terms to get these terms here. And then we put the like terms together. So we put the TF terms on one side of the equation and the rest on the other side of the equation. And then since there's a TF in both of these, we take the TF out here, and then what's left is C1 plus C2, and then we divide both sides of the equation by C1 plus C2. So we get our final temperature is equal to C2 times T2 plus capital C1 times T1 divided by C1 plus C2. So make sure to go through that and see how that algebra was performed there. So if you have to do a problem that requires a thermal equilibrium, you'll have the equation to do that. Next, we'll look at heat capacity. Heat capacity is the amount of heat required to raise the temperature of a mass by a certain amount. Heat capacity is a function of what a material is made out of, whether it's a rock material or a water material or air. Every substance has a different heat capacity. For example, the heat capacity of land versus the heat capacity of water. And on the overhead, we'll take a look at an example of that. This is a sunny summer day. So we have the same amount of heat coming from the sun and warming up the land and the water surface. But the temperature above this land and water surface are often going to be different. And that is due to this concept of the heat capacities are different for different substances. The water can absorb a large amount of heat, and water, since it's in freer motion than land is, it can mix that heat down towards further down into the water. While on the land, most of the heating is going to be done in the shallow layer right at the top of the land, or in the water, the heat can mix down. You also have evaporation on the water surface, especially if it's a dry, sunny day. You get evaporation that takes place, and that will promote some evaporational cooling. So there's several processes that are occurring that cause the temperatures above the water to be cooler than over the land on a sunny day. And this is assuming, too, that the water and the land start off at about the same temperature. And then over time during the day, as the sun's out, the land is going to warm up more than the water. Next, we'll look at the first law of thermodynamics. And that tells us that energy is neither created nor destroyed, but energy can change forms. The equation for the first law of thermodynamics is the change in heat is equal to the change in internal energy plus the change in work. Example, heat added to an air parcel by compressing it or conducting energy into the air parcel. Another way to write this equation is the change in work is equal to pressure times the change in volume. The work, change in work done by a body of air when its volume increases is equal to the pressure times the increase in the volume. And another way of writing that is the change in heat is equal to the change in internal energy plus the pressure times the change in volume. That's another way of writing the first law of thermodynamics. A very important concept is the adiabatic process. In the adiabatic process, we start off with a parcel of air, and that parcel of air will have an initial temperature, it'll have an initial amount of moisture, an initial pressure, volume, and mass. And a huge assumption is that the parcel does not mix with the surrounding air. Many of the parcel variables of this parcel are going to change when it rises or sinks. So we can use the skew-T log P diagram, and we can use the theory that we're going to go over with to predict the temperature change that will occur in a parcel of air as it rises or when it sinks. If the parcel of air is dry, and by dry we mean that the parcel of air is unsaturated, it could still have some moisture in it, but as long as the relative humidity is not 100%, as long as the relative humidity stays at less than 100% in the parcel is going to cool at the dry adiabatic lapse rate when it rises, and it's going to warm at the dry adiabatic lapse rate when it sinks. So the rising air cools, sinking air warms. The equation for the dry adiabatic lapse rate is the change in temperature with the change in height is equal to a negative gravity constant divided by the gas constant at a constant pressure. So the negative sign is there because the temperature is decreasing with height. Normally when graphing, when you go up on the y-axis, it's a positive value, you're increasing values, but that's not the case with the change in temperature with the change in height. It decreases as you go up, so that's where the negative sign comes from. G and Cp are both constants, so since we're taking two constants and dividing them by each other, then the dry adiabatic lapse rate is also a constant. So if the air is unsaturated, its rate of cooling and warming, depending on if it's rising or sinking, is going to be at a constant lapse rate. And this lapse rate is 9.8 degrees Celsius per kilometer. And on the overhead, we'll take a look at this equation and how the units work out in the dry adiabatic lapse rate equation. So we have gravity divided by a constant pressure process, a gas constant. So the gravity is meters per second squared, and CP has units of joules per kilogram per Kelvin. So we can write a joule as a Newton times a meter. So it's a kilogram meter per second squared times a meter. And then we have the kilogram and Kelvin to the -1. The seconds to the -2 cancel each other out. These 2 kilograms, you got a kilogram times a 1/kilogram. Those cancel each other out. 2 of the meters cancel each other out. You got 1 at the bottom, 1 at the top. And so we're left with just units in the denominator, a meter and a Kelvin. We can move this Kelvin up to the top, and when doing that, it's going to change the sign. So we're left with units of Kelvin per meter. Since the Kelvin has the same increment of temperature as Celsius, we can write that as Celsius per meter. And when in operational meteorology, when we use lapse rates, we simplify this by writing it in degrees Celsius per kilometer. So since there's 1,000 meters in a kilometer, we take the degrees Celsius per meter, multiply by 1,000 to get our lapse rate of degrees Celsius per kilometer. And again, that number is 9.8 degrees Celsius per kilometer. Next, we'll look at potential temperature. This is one of the first concepts that we need to go over in being able to understand what an isentropic process is and how to read isentropic charts. Potential temperature is derived from the first law of thermodynamics. And the equation for the potential temperature is to take the temperature and then multiply it by 1,000 divided by the initial pressure, and that 1,000 divided by the initial pressure is raised to the power of RD divided by CP, which are 2 gas constants, which comes out to 0.286 power. So the potential temperature is the temperature that's found after air is moved from its initial pressure to the 1,000 millibar pressure surface. And we're going to be moving it along the dry adiabats also. So when we're doing this isentropic process, we're assuming that the air is unsaturated. So it's going to follow that 9.8 degrees Celsius per kilometer as it's rising or sinking. The potential temperature equation is also known as Poisson's equation. The potential temperature, or lines of it, are also called isentropes or theta. So when you're reading forecast discussions, you'll often come across the term isentrope or theta and know that that has to deal with an isentropic analysis. Also, the solutions to Poisson's equation form the dry adiabatic lines on the skew-T log P diagram. And on the overhead, we'll take a look at a skew-T log P diagram. And you'll have this with you so that you can see this close and up in detail. These lines here that are sloping upwards and to the left are the dry adiabats. And notice that they're fairly straight on the diagram. because they have that constant lapse rate of 9.8 C per kilometer. So when air rises and it's unsaturated, it's going to rise along these dry adiabats. So whatever the initial temperature is, let's pick a point here. It has the initial temperature. If we raise that parcel up, it's going to cool off at the dry adiabatic lapse rate. So it'll be parallel to the nearest dry adiabatic lapse rate. If it sinks, then it's going to warm at the dry adiabatic lapse rate. So we can use the skew-T log P diagram to determine how much a parcel of air is going to warm or cool as it rises or sinks. And to find that potential temperatures, we take our parcel of air wherever it is on the sounding, so we have an initial temperature and pressure, and then bring that down to the 1,000 millibar level and read off what that temperature is once it's brought down. So the only reason why we're bringing it down to 1,000 millibars is we need a reference level to compare parcels at. We'll look at some more on potential temperature. Potential temperature theta, as I mentioned, is the temperature a parcel of air will have if raised or lowered to the 1,000 millibar level. And it's usually going to be lowered, since most of the sounding is going to be above or have a lower pressure than 1,000 millibars. Potential temperature is the same for a parcel of air as it rises or sinks, assuming adiabatic conditions. Now, the actual temperature of the parcel is going to change as it rises or sinks, but its potential temperature is going to stay exactly the same. As long as that air parcel stays on the same dry adiabat, it's going to have the same potential temperature. Next, we'll look at how to find theta using the skew-T log P diagram, how to find the potential temperature. When reading forecast discussions, when they're talking about the theta value, they'll almost always give it in the units of Kelvin. So if you wanted to convert that to a Celsius temperature, you take the Kelvin value and subtract 273. And then if you wanted to further put it into units of Fahrenheit, you could do that also. At 1,000 millibar pressure surface on the skew-T and starting at a specified theta value, go up at the dry adiabatic lapse rate until sounding is intersected. That intersection is the height, the elevation pressure surface for that theta value. And we'll go back to the overhead to take a look at what process I'm describing there. When you look at an isentropic chart, one of the first things you need to look for is what theta value that chart is for. So our example here, we're going to find what is the elevation pressure surface when the theta is 292 Kelvin. So that's a critical piece of information. We know what our temperature is here, 292 Kelvin. And since Kelvin's not given on the skew-T, only Celsius is, then we need to convert that to a Celsius temperature. So we take that 292 and subtract 273, and we get 19 degrees Celsius. So we start at the 1,000 millibar pressure surface, and on the skew-T log P, pressure is given on the far left side, starting from 1,000, and as you go up higher into the troposphere, the pressure decreases. Since potential temperature is measured with respect to the 1,000 millibar pressure surface, we need to start at 1,000 millibars. And since our theta value is 292, 19 degrees Celsius, the point that we want to pick is 19 degrees Celsius at the 1,000 millibar pressure surface, which is going to be at that location there on the skew-T log P diagram. And then next, it's like finding the potential temperature in reverse. Next, we take this location and raise it up parallel to the dry adiabatic lapse rate. We do that and eventually we'll intersect the sounding. Where we intersect the temperature sounding, what that pressure level is known as the elevation pressure surface. And the elevation pressure surface in this case is 875 millibars. 875 millibars, which is about right there. If you drew from the point that we intersected the sounding, if you drew a line straight across and read off the pressure, it'd be 875 millibars. So see, it's find the potential temperature in reverse. If we had a point on the sounding there and we found the potential temperature, we'd lower at the dry adiabatic lapse rate till we get to the 1,000 millibar pressure surface and read off that temperature. And that would come out to be 19 degrees Celsius, or 292 Kelvin. Next, we'll go over the isentropic analysis, now that you know how a potential temperature is found. An isentropic analysis is the use of theta charts, wind charts, and mixing ratio charts to help determine if a layer of air will lift, sink, or stay at a constant altitude in a differential advection situation. And what's meant by a differential advection situation is a situation in where you have, for example, a shallow cold air mass near the surface, and you have warm air that's overriding that shallow cold air, and it's overriding that colder air at a slope. So the isentropic process most commonly occurs in the cool season when you have shallow fronts that move into the United States. But it can happen in any situation also when you have two different air masses flowing over the top of each other. So with a warm front, if you're analyzing the lifting occurring on a warm front, a good idea would be to use an isentropic analysis. And this information in the isentropic analysis, we're figuring out what's the potential there for how much the air is going to rise as it's moving, or it could sink too. It's a dynamic rising or sinking motion. And this information can be used to help assess the precipitation threat. We're going to start with going over how a theta chart is developed. The chart is based on a constant value of potential temperature. As I mentioned, anytime you see a potential temperature chart, look and see what that value of potential temperature is for that chart. The elevation or pressure level at theta is reached is contoured on the chart. To understand how a pressure level is determined using a theta surface, we will examine the skew-T log P diagram. So we'll go back to the overhead and look at our problem that we were doing before. To refresh your memory here, that we were looking at a 292 Kelvin theta surface, which was 19 degrees Celsius. So we started off at 19 degrees Celsius, 1,000 millibars, and this is the Jackson, Mississippi sounding. And for this sounding, we go up parallel to the dry adiabatic lapse rate until we intersect the sounding. At that point that we intersect the sounding is the elevation pressure surface for that sounding using this theta value of 292. And each sounding is going to potentially have a different value because this sounding could be cooler. Suppose that all the temperatures in the sounding were cooler, then this elevation pressure surface would be higher up. You'd have to raise it up further before you intersect the sounding. Or if this whole sounding was warmer, then you would not have to go up as high to reach the elevation pressure surface. So this skew-T log P diagram from Jackson, Mississippi is just one point on our chart that we're going to develop, our theta chart. And again, we found that elevation pressure surface is 875 millibars. So next, we'll look at a theta chart. This theta chart on the top left, it has 292 Kelvin as our theta value. And these elevation pressure surfaces are contoured on the diagram. And I've darkened those in to highlight those for you. Well, here's the 900 millibar pressure surface, here's 875, here's 850, and here's 825, and so on. Now for 1 point for Jackson, Mississippi, we found on that sounding that it's 875. Jackson, Mississippi on the diagram is located right at this point there, where I've darkened that point in. And notice that that point is right on this 875, and this is in millibars. So this is different from a pressure. This is an elevation pressure surface. So don't think of this as like a surface pressure or anything like that. It's done a different way in an isentropic analysis. So that point there that we found on the skew-T log P diagram in Jackson, Mississippi corresponds to this 875 millibar pressure surface. So imagine that there's soundings taken all over the place, all over the United States, and every one of those soundings is going to have a different elevation pressure surface potentially. Especially if you go up to the north, you're in colder air here. The air's colder. So that parcel of air needs to be lifted higher up before it intersects the sounding. Again, if we had this Jackson sounding, and imagine that the whole sounding was colder, then if we start at the 292 Kelvin theta surface, we'd have to lift it up further before it would intersect the sounding. So you end up with going up higher into the troposphere, so ending up at a lower elevation pressure surface. If the sounding was warmer, then we would not have to go up as high. We'd intersect the sounding very quickly. And points further down toward the south, that's the case, such as New Orleans. The sounding is warmer, so you don't have to go up quite as high for that 292 theta to intersect the sounding. So now you see how a potential temperature chart is developed and how the skew-T log P diagram is used to put the points on there and then connect the values of equal elevation pressure surfaces. So we picked 292 Kelvin, but how do we know that that is the best value to use? A rough guide here, theta by season, is that in the wintertime, you're going to want to use a colder value for theta. And in the summertime, you're going to want to use a warmer value. And I can give you some websites. I don't give them in the lecture because often websites change, but online within the course I can give you some current websites where you can look at these isentropic charts, and it allows you to pick the value that you want. So if it was the winter time, you could pick 285 Kelvin if you wanted to. And in the summertime, you could pick a higher value. You want to pick a value where you're assessing a lot of the lower troposphere. Because if you don't pick the right value, then either it's intersecting your sounding too high up, or it's not intersecting your sounding at all, and you're not going to get as good an information, because usually in these differential advection situations where the lifting occurs, it generally occurs in the lower troposphere. Next, we'll look at theta mixing ratio charts. Theta mixing ratio charts show the mixing ratio contours on the theta surface. This allows for the assessment of moisture advection on the theta surface. The mixing ratio is the mass of water vapor divided by the mass of dry air. So it gives us an indication of how much moisture there is in the air. Like dew point, it's a good comparative value for how much moisture that there is in the air. And on the overhead, we'll take a look at that same chart that we were looking at before, but also given on this same chart, we went over the elevation pressure surfaces that are on there. There's another contour, and I've highlighted this one separately on the chart, is the mixing ratio, which is in grams per kilogram. And along the bottom here, if there's not much shading, that indicates the air does not have a lot of moisture in it. And if it's a high value, really darkened in, that indicates that the air has lots of moisture in it. Now from the chart that we were looking at earlier, as you go up to the north, your elevation pressure surfaces are going higher up, so your temperatures are a lot colder up here too. So that's one reason why it's not indicating as much moisture in the air up here, because this is going up higher into the troposphere. You have colder air. Well, down here to the south, you're assessing air that's closer to the surface, and it also has more moisture in the air too, because you have moisture from the Gulf of Mexico. So we've contoured our mixing ratio values out here. 14, 16 grams per kilogram indicate a significant amount of moisture in the air. And as you go up to the north, there's less and less moisture. Because I mentioned you're going up higher into the troposphere, and there may be just less moisture within the troposphere also. Because if you have warmer temperatures, that's going to support the evaporation of more moisture into the air. So if you have warm air, it's often going to have more moisture than cool air, even if there happen to be both at the surface. Next, we'll look at theta wind charts. So we got two ingredients that we've looked at so far, the mixing ratio and the elevation pressure surfaces. The last component is the wind. The theta wind chart. Wind charts on a theta surface are used to show where moisture is being advected and whether the air flows up, parallel to, or down the theta pressure surface. And on the overhead, we'll take a look at some wind vectors that I've darkened in here. All across the diagram you see these little wind vectors, and I've darkened them in the area that we're interested here in the southeastern United States. Near the Gulf Coast, we have winds coming from a southerly type direction. So we have moist air here from the Gulf of Mexico, and it's moving up towards the north. And doing an isentropic analysis, we want to figure out how much that air is lifting, or if it's sinking, or neither one. So this chart that we've been looking at is known as a composite theta chart. A composite theta chart will overlay the mixing ratio values, the wind vectors, and the pressure surfaces using a constant theta surface. This is the same chart we've been looking at. On each one, I've darkened each of the contours on there. And now we want to put all of it together to figure out if there's going to be an isentropic motion and what that isentropic motion is. So we'll go back and look at a chart where I have nothing darkened in on here. So we have most of our moisture here using the 292 theta surface. We got a lot of moisture here near the coast. And the wind vectors that we saw before were moving out from the south near the coast, and we have elevation pressure surfaces that were like this. So in this region here, we have the air that's moving from a higher elevation pressure surface, and put back the elevation pressure surfaces there, where it was 900 millibars, and this air is moving from the south up to a lower pressure. So that's an indication that the air is rising. So if the air is moving such that it's moving toward an elevation pressure surface that's higher up in the troposphere, that tells us that isentropic lifting is occurring in that air. Up in northern Mississippi, Alabama, and Georgia, the wind direction is fairly parallel to the elevation pressure surfaces. So there's not as much isentropic lifting occurring here as there is down here. And this air on this day was fairly saturated down here in the Gulf, so any kind of lifting of that air is going to generate precipitation. So it generated widespread precipitation here on the Gulf, where that moist air was being isentropically lifted. So another way to think about that is think to the north as you have cold, denser air, and to the south you have less dense, warm air. This less dense air is not going to want to go underneath this more dense air. It's going to want to ride above it. So it moves along the isentropes in order to do that when it rises. So you got flow coming from the south, rising up, and then as it gets further to the north, it's not rising as much. So we definitely have an isentropic motion there. So a meteorologist in a differential advection situation where you have different air masses that are close together will look at these isentropic charts, pick the best level to assess the isentropic chart, and see if the air is rising or sinking. Next topic that we're going to look at is the hypsometric equation. The hypsometric equation is derived from the ideal gas law. And this is an extremely important equation in meteorology because this is what is used to develop all the height contours on the upper level charts. It comes from this equation. This equation is used to find the thickness, the distance between two pressure surfaces. And on many of the charts that you look at, 850, 700, 500, 300 millibar charts, that's the distance from 0 geopotential meter up to that pressure surface. And then it's contoured out. The thickness value, or the geopotential height, is a function of the temperature and moisture content of the air, with the temperature being the most important influence. The solutions to the hypsometric equation can be used to help forecast precipitation type, thermal advection, and temperatures. We'll take a look on the overhead at the hypsometric equation. It has a delta Z, which is the change in thickness, the distance between two pressure levels. And that's found with RD, a gas constant, times the virtual temperature. Virtual temperature is used so that we're assessing the moisture that's in the air, and we'll go over what the virtual temperature is, divided by gravity times the natural log of P1 divided by P2. So if we had a thickness increase, then often that's accompanied with a warming. A warming has taken place. So this is the surface, and suppose that initially the 700 millibar level is here. after warming takes place. We'll assume that there's been some warm air advection or some solar heating. But after this air warms up, the air becomes less dense and it expands. And thus the pressure surfaces are going to rise upwards. So the 700 millibar level will rise up, for example, a little bit higher here after that warming takes place. So in our hypsometric equation, we're finding what the distance is between two pressure levels. And that's mainly going to be a function of the temperature of the air, with moisture being a secondary influence. It's mainly the temperature that's most important. Here is the hypsometric equation, an example. We're going to do an example of finding what this thickness is between 850 and 700 millibars. So we take our two constants in the equation, divide them by each other, and then we need to know what the virtual temperature of the air is. And then we multiply that by the natural log of P1 over P2. The natural log of P1 over P2, you take 850 divided by 700, take the natural log of that, and you get 0.194156. So we've reduced this all down to numbers, except we need to put the virtual temperature in. Suppose that the virtual temperature is 5 degrees Celsius. You have to convert that to 278 into Kelvin before putting it into the equation. It must be in units of Kelvin. So once it's put into the equation, these terms are multiplied out, we get a thickness of 1,581 meters. Next, we'll look at the second law of thermodynamics. And that tells us that the direction of heat flow is warmer toward a colder substance, warmer toward colder. Not all heat can be converted into work due to inefficiencies in the system. And these inefficiencies are called entropy. That's covered in the book. We'll look at an overhead. So you can visualize this process, the direction of heat flow. Anytime you have a warmer substance next to a colder substance, you're going to have a heat flow. For example, suppose you're in a room here, and this room is warmed by a heater, so you have warm air inside the room. But this is a cold winter day, and outside you have cold air. So the direction of heat flow is going to be from the warm air towards the cold air. So you're going to lose some of your heat to the cold air, and then you have to turn the heater back on. The heater keeps turning back on to make up for the heat that's lost. Next, we'll go over what a reversible and irreversible process are. First, a reversible process. It is a process in which a system and the environment can return to the original state after a thermodynamic process takes place. An example is unsaturated parcel rising, then returning to the original location. An irreversible process, that's a process in which a system environment cannot return to the same thermodynamic state without being influenced from an outside force. Examples: an air parcel losing moisture over a mountain and then returning. On the overhead, we'll take a look at an example of a reversible and irreversible process with the parcel of air moving in the atmosphere. First, with the reversible process. The potential temperature is a reversible process. Is if the air keeps the same potential temperature, then it's a reversible process. The air can move up and down the dry adiabats, and it can return to the original temperature and dew point that it had. So suppose that it starts off, we have a parcel of air near the surface, it's 80 degrees, and a dew point of 70 degrees. And suppose that we lift that parcel up. As the parcel rises, it's going to cool. And we lift that parcel up, And suppose we lift it up and we cool it off to a temperature of 70, and then the dew point decreases down to 68. One interesting thing about dew point is that it actually does change as a parcel of air rises or sinks, although the amount of moisture in the air is very similar. The dew point does actually change. But although the dew point changes as it rises, if we brought it back down to the same location, the dew point would go right back to 70. So this air with 80 over 70, we rise it up here, it changes the temperature and dew point, and then that air drops right back down, and we have the same temperature. And also the surrounding environment cannot change also. In an irreversible process, it cannot return back to its original state. An example of that is, suppose we have air that has a temperature of 50 with a dew point of 42. And we lift that air upwards until it becomes saturated. We lift it up and it becomes saturated. We lift it up further. It generates clouds and precipitation. At the top of this mountain, it's 30 over 30. So as it's risen, when it first started rising, it was cooling at the dry adiabatic lapse rate. Then it becomes saturated when the temperature is equal to the dew point, and then it cools at the moist adiabatic lapse rate at that point. And suppose that we have 30 over 30, it's saturated. Then on the other side, it sinks back down and warms at the dry adiabatic lapse rate all the way from the top to the bottom of the mountain. Now, if we want to take this parcel of air and move it back to where it originally was, you will not be able to get the same temperature and dew point because we've lost moisture from the precipitation process as this air was rising. So we can't get that moisture back. So if we're 60 over 36 and we took this parcel here and then went in the reverse process, when it got back to the other side, it would still be 60 over 36. You couldn't get back to this 50 over 42 since the parcel of air has lost moisture in this process. In our next lecture, we'll look at the thermodynamics of water vapor and moist air, and that will do it for today's lecture. I'll see you next time.